Okay, well, so let me see. In terms of questions, let me see who would like to go first. And we actually, I'm really excited. We had David Chester show up too, which was really cool. So let me see. Who would like to? Oh, Remy, go for it, sir. Oh, sorry about that. Okay.
Can you hear me now?
I can hear you, yes.
Thanks, Kenneth. I can't say I understood much of that, maybe 1% of it. I think it need to be, graduate level physics. But I just got a question for you. Do you believe do you believe in warp drives, faster than light, Maxwell demons, all this stuff which is stock and trade of this forum? Or is it just going to be sort of another sort of brick in the wall where the establishments are saying no, 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 and we're going to make it so complicated that you can't understand it and you can't answer back?
That's an excellent question. Now I don't know about I know that the warp drive stuff, but you said something about demons. I didn't quite understand that.
Oh, Maxwell's.
Oh, Maxwell's demons. Oh, okay, I gotcha. Thank you. Yeah. So the answer is yes. Okay. Yes, we explain warp drive. Yes, we demonstrate how quantum gravity actually enables you to create Alcubierre warp drive. We explain what we mean by negative energy, and all of it is as simple. Okay, I know that this was a lot of math at you right up front, but I challenge you to just read through the description again. If Tim can upload the presentation, which I'm probably sure he will, but just to walk through it again in your own time, look at some of the sources, and I guarantee you're going to discover very quickly that this math is beyond easy. But the point there is because the math is easy, then that enables us to actually describe and to define what the heck do we mean by warp drive in an equally easy manner. This is not difficult.
I'm having trouble linking this to physics we know. I mean, can you give them what I've got in my head? I've got, say, something like a scattering process. So I've got on the left-hand side and I've got on the right-hand side.
Yes.
And you're simply, what you're saying, it's almost like a linguistic manipulation. You're manipulating these symbols in all the permutations they could possibly take on the left-hand side and on the right-hand side. And you're saying it's only meaningful if there are some underlying rules. And when you get these rules, you suddenly output things like conservation of energy, covariance, and things like that. That's essentially what you're saying, isn't it?
Yes, I think it's more sophisticated than that, but yeah, I mean, in a nutshell, what we're saying is that the general principle that underlies all of our equations is the principle of general covariance. And we realize that from this general principle, we can derive quantum field theories, we can derive general relativity theory.
Yeah, but when you say covariance, straight away, isn't that a limiting belief? Because when you say covariance, that's automatically meaning you can't travel faster than the speed of light.
No, not at all. Not at all. That's not what it means. No.
What is covariance then?
So what covariance is saying is that effectively all of our systems do not have a predefined coordinate system. That the coordinates, and so that
I agree. It's the usual definition of diffeomorphisms and all that. Yeah,
that's right.
Continuously differentiable manifolds and all this, and how you can relate to one aspect of physics or one coordinate system to another. Yeah, that's the usual definition of covariance. Yeah.
That's okay. Right. And so just based, sorry, go on.
What new is coming out of this? I mean, this is just not to be dismissive. I mean, I don't know if you saw in the chat, but I gave Feynman's recollections would be the right words, on when he moved from undergraduate to graduate school and suddenly had to relearn everything.
Yes.
So instead of using this, say, forces and do all this, he had to learn things the variation of way. And he took all his homework and converted it to just a sort of Newtonian understanding. You couldn't see the point of it, and then the penny dropped. And then Benny saw the utility of variational methods. It was much better. It was a much more elegant system, which allowed you to do more things. That's what you're trying to say, isn't it? Is that what you're trying to say?
I mean, I basically say that, yes, we are finding a different mathematical description that actually gets to the heart of what the heck do we mean by measurement in the first place. I think that a lot of the things that we've been doing, sorry, go on.
Yeah, that's important. Yeah, sorry, I'm just whittering away. Yeah, that's important. Yeah, the measurement problem. Yeah, yeah.
And so
And the loss of entanglements. You know, how things become entangled with the environment and so forth. Yeah, these things are really well understood. Yeah.
That's right. That's right. And in fact, in this different way of seeing it using combinatorics, we're able to define is what the heck do we, I mean, obviously in quantum mechanics, we can define very easily what we mean by entanglement. But here we're actually able to define it in a very different way. And in this particular different way, the edges that exist between our vertices, for example, in our graphs, which we really didn't introduce structurally here. We just sort of, marked at it.
Are you talking about Feynman diagrams? And when you talk about vertices, is that what you mean? Feynman diagrams?
No, not exactly those vertices, although it still does apply there too. Generally a Feynman, so when we were talking about the cyclic generating function, the thing I was calling GT, and then the permutation generating function, the thing I was calling PT. The cyclic generating function is what we utilize in every imaginable way in Phoenix, because it is a sort of a binary language or what do we call it, the game set. It's where you put all the little pieces together and you build whatever.
You're saying kind of like a foundational building block, essentially.
Yeah,
right?
yeah, exactly.
You mean like
Jenga tower.
Lego.
Like a Jenga tower, exactly. And the reason why I mention that is because the way we do field theory is that we don't consider that there are any actual relevant building blocks, sort of fields. And what Phoenix is saying is that's not true. There are actually sort of a binary system of building blocks that can generate a field. And the reason why that's so important here is because with Feynman diagrams, we're talking about a field representation of particle physics. Phoenix can give you that. But what we're really talking about in Phoenix is literally a Jenga tower construction where we're not dealing with fields on that level. We're dealing with, little Hershey's Kisses as opposed to, Willy Wonka's vat of chocolate. But the Feynman process utilizes permutations all over the place in order to generate our understanding of modern particle fields. But we're showing you that no, there's a more basic language structure, a more basic alphabet. So the idea is how do you go between the two so that we can actually generate, once again, Feynman diagrams. But we start off with a basic building block system.
Well,
What are your deliverables? Sorry to cut in. What are your deliverables? Where are you taking this? Speaking from a sort of physics engineering background,
Sure.
is the utility of this? What are you gaining from this? I know you said it's a more simple description.
That's the first, yeah. That's a critical part. Well, the reason why, sort of this particular approach, it's like asking, how do I want to understand how Microsoft Word works? Do I want to understand it by using the program over and over and over, or do I want to go to the code? So if someone could have handed you, that's probably not going to help either since there's, a billion lines of code. But nevertheless, if you really wanted to understand the system, you're not going to try to figure it out by using Microsoft. You're going to try to understand it by reading the code. So what we're providing is the actual code. And what we're also demonstrating is that the code gives you the most efficient, obviously that's why we try to get down to the smaller parts, but the most efficient language for creating this thing that we call, Microsoft Office, or for this thing we call a quantum field, which we do not have.
To use your analogy, between Microsoft Word and the computer program itself, using it would be like an experiment.
most efficient language for that language. Is that what you just said?
Okay, can you say that again?
Oh, sorry. Yeah, that was Bernie. But
Hi,
Bernie,
Bernie.
can you repeat that? I think he's saying the most efficient way, the most efficient language to describe the basic concepts. I think that's what Bernie's asking, right?
It just sounded like you used the definition of a word to describe it. That's all.
Are you saying that? Mhm.
Anyway, I'll get back to the point I was making. To me,
Yes.
your analogy with Word, say, the person who finds out how it works is like the experimenter. Yeah, the person looking into it is like the theoretician, who's looking into the code. Yeah,
Yeah.
is that a good analogy?
No. But we're also saying that the experimenter can find this too. Our experiments are not limited to quantum fields. That's my, if you want to have another sort of takeaway from this, yeah, there are actually more efficient mechanisms for digging up why particles do what they do, other than the means that we use to do it now, which are, of course, our particle accelerators. In other words, our field scattering experiments. This gives you another way of arriving at exactly those same conclusions, or whatever, wherever nature is leading you, looking at the building blocks themselves, as opposed to, someone giving you the Lego, the museum of Lego statues.
Is there
That's great.
Is there anything that you might rule out? Because, there's a lot of experimentalists here, and they're thinking, oh God, more theory, having to sit through lectures. And one of the things we've all sort of come across is when the teacher says, you can't do that because I said you can't do that, and you find some way around it, that they think they have an all-encompassing theory, but there's a hole in it somewhere, and theory breaks down.
Yeah. So, so the idea that a good example of what we're talking about with Phoenix is that the idea of the speed of an object that we represent in relativity theory as beta, right? Your speed divided by the speed of light. Yeah, right. So that concept for us is a thermodynamic concept. So it's like temperature. In other words, it doesn't really live at the level of the true quantum. It doesn't live at the level of an alphabet. It is how you scale from your alphabet into, the creation of a word or the creation of a sentence or whatever. But it's not a fundamental thing. And where that lands us is in complete agreement with why relativity theory is not at the same level as quantum mechanics. Quantum mechanics is at a deeper level than Einstein's general theory of relativity. And so this completely agrees, because the marker, the tool that enables you to explore relativity theory, namely beta, in our case, beta is Z. So every time you see a Z, that's beta for us. So but it only lives as a continuous variable that takes you from a microcanonical world into a macrocanonical world. But that's where it doesn't really have a true existence at the most fundamental level.
Well, I think
in other words, at the most fundamental level, our proton, for example, does not have a relativistic speed.
Yeah.
It has a momentum. It's got a chunky quantum mechanical momentum, but no continuous relativistic speed. Okay. And that's a huge, huge understanding. Yeah.
I would probably try to break it down into sort of primers for different levels. Yeah. Because I can just about connect with what you're saying, at graduate level, but to break it down for, say, engineers and people not even at university level, it's not really communicating. I've seen this many times with theoreticians. So they're in an ivory tower, yeah?
Okay, so a way of making it communicate is this. The space you see around you, I think everybody in this room probably agrees, but the space you see around you is not continuous. It's chunky. And it's even more dramatic than that. So when we talk about the number of vertices that a particle has, what we're really saying are all of the true degrees of freedom that particles can possess. But what that means is that in the universe around you, the number of degrees of freedom that you think exist is much, much smaller than what you think you're experiencing. It's more or less a holographic idea. But what that means is that space itself can actually bubble. Space itself can actually, the chunky part of space can be made to resonate with each other parts of the chunky part to form regions of space that actually look like bubbles to us at our level, under certain circumstances. But the idea there is that there's a whole different way of understanding space, such that space itself, for example, can be described by fluid dynamics, and that fluid dynamics can actually create turbulence. Space isn't always laminar, okay? And you can utilize that turbulence of space in order to, for example, undo gravity. Because what we mean by gravity is really how space and matter are actually interacting with each other. But if I can resonate that any structure in the space, then I can get space to phase. I can get it to change from the form that we commonly think about, which is smooth and laminar, into something that looks much more chaotic. And when it does that, gravity itself breaks down. So that's an example, I think, of.
Okay.
I would pitch it as sort of good engineers level, good graduate student level. You need to sort of communicate the ideas before they taken up.
Yeah.
It's
Well,
all,
Remy, let me
isn't it?
let me jump in. I want to try and go to Jeremy Reese if it's okay, because we're starting to get some questions piling up.
Okay.
So let me go to Jeremy Reese next.
Hey, Jeremy.
Okay, Jeremy.
Hey Ken, welcome back to the Alien Scientist channel, and thank you for that presentation.
Well, thanks for inviting.
This is did Wolfram inspire you at all to come forward and share more of your ideas? Because I've got a couple good comments from one of my friends, Carl Cartesian. He's been into my channel since the Hover Brothers and that whole thing with theories of everything, and he's been big on following Wolfram's work. He says, when you say these cycle generating functions, is that in any way analogous to Wolfram's concept for slicing the multi-wave hypergraph as a measurement of time?
Absolutely. The beauty about Wolfram is that, he's been, attempting to divine, how do we, algorithmically talk about space, time, and matter, and then hopefully, quantum mechanics and relativity theory emerge from it. And so, yeah, the notion of, slicing up he's going to misrepresent and call it a multiverse, but slicing up his causal universe into these variations or into these slices is what generates special relativity theory, is really, in fact, kind of what we're talking about, definitely. But yes, I was certainly inspired by his work, because that's exactly the conclusion that we're coming to. The universe is an algorithm, and that algorithm has well-defined lines of code. Those well-defined lines of code encompass what we call the laws of nature. And if you want to understand structurally how nature can become altered or transformed, because you're looking at it, through a quantum mechanical way of seeing it, into something slightly different, then both of these approaches are trying to reach that end. So our algorithm is really the generating function. It's what we would call the program. Each line of code of the program is marked by z squared, z cubed, each of the different parts of that generating function. And each one of those parts talk to each other. So the lines of code can, spit out a piece of information that goes to the next line, and it can spit it right back up. So it is a program as well as Wolfram is playing with, definitely, or more than playing with, studying.
So now describe more about how entanglement works its way into the picture, because you had mentioned before, we talked about spatial and temporal entanglement. And what does it mean when things are you have an entangled system, and then what does it mean to have when systems obviously become disentangled or entangled elsewhere? And kind of, I don't know, I kind of want to understand more about this temporal and spatial entanglement
Okay.
and how it works into your theories and that you just showed.
Okay, so the easiest way I think of thinking about it is in terms of our graphs. And the question is, what, you know, I didn't really show you a picture of, and you've seen too many of them, but I didn't show it generally for everybody what we mean by a graph, which is just a series of vertices that are connected through edges. And sometimes the vertices themselves can be connected to themselves to form loops or arrows. But the point is that the vertices represent all of the different configurations of information on a network, okay? And those different configurations of information can actually be conjoined with each other. So for example, if you look at eddies that are formed in a fluid, they don't just sit by themselves. After some time, the eddies will begin to congeal, and sometimes they may even begin to fall apart. Information flows in exactly the same way across any network. There's going to be sometimes disturbances between different information flows. The question is, can that actually be codified? And what we're saying here is, yes, absolutely it can. Our evolution equation that we said there's a transformation on some system and it becomes another system with a transformation matrix, that's an evolution equation. But our evolution equation just marks out how vertices can be conjoined with each other over a marker of time. What's allowed and what's not allowed. So the conjoining of vertices to form what we call a graph, okay? That conjoining is what we mean by those vertices are entangled. So if you've seen our diagram of a proton, it has two loops, it has one loop in the, so there are three vertices, and they're all connected in a line. There's two loops, two vertices on either side that have two loops on them, and one vertex in the middle that has a single loop on it. And that particular structure is what we call a proton. But what it's really showing is that you have three parts of information flow that are somehow hooked up to each other, and they don't want to let each other go. And the way we see that even more, and I can, you know, it looks like a dumbbell with a loop in the middle, but the point is that what you're really seeing is two up quarks, the two things on the ends that have two loops on them, and then a down quark, the thing in the middle that has one loop on it. But what you find is that that is a stable information configuration. Now, what we can do when we, if I'm invited back, is to explicitly show you a network and how the information flowing on that network resembles these different patterns of information that I'm talking about, like the proton and the electron and the neutrino, etc. And then how those things are allowed to combine and disconnect from each other. And that's what we call particle reactions in Phoenix. So when we do a calculation of probability, particle reactions, we don't do long drawn out scattering theory processes. We don't. All we do is you tell me what the configuration is that you initially start with, let's just say a proton, or let's say a neutron. And then this will, in one step, bring you to a proton and a W minus or a chi minus particle. So it's a very, very simple, efficient, and elegant methodology for establishing why particles change. Why do they combine up or disintegrate and break apart? And then when they do break apart, why do some things remain stable? They don't seem to break apart anymore. And it's because it's not allowed in this, in the evolution equation. It's just, there is no evolutionary step that will take a proton into anything but a proton. So if you go out to the regular quantum field theory world, you know, where we're actually using Feynman diagrams, and we're using quantum electrodynamics, and then quantum chromodynamics, and then quantum, the extension of electrodynamics into the weak system. But the point is, if you do that, there's a contradiction that arises. We have proton decay, and we can't explain it. We've literally set up experiments all across the world for billions of dollars since the 1970s that cannot tell you why the proton is stable. All it can do is to keep pushing back how long the proton lives. I think at this point we're like 10 to the 40th years or something. So the idea is this one explicitly says in one step, the proton is stable. You can't break apart. There's nothing you can do. It's going to be sticking. We can even go forward to show you how the proton and the neutron can actually bind together and how they can fall apart after they've bound together. In other words, nuclear theory. So we have very explicit representation of how you get these other manifestations, whether it's the atom, whether it's the nucleus, whether it's, muons possibly being emitted by nucleons, and what effect that has on the nucleus, etc. But we can get these explicit representations in very, very small ways from this Phoenix way of looking at it.
Now, Ken, if I could jump in really quick,
Sure.
and this is something Remy had asked chat, but I'm also interested. What are some of the predictions, I guess, the Phoenix theory would make? Because I know there are many, and I think this is one of the reasons that people get so excited about it. What are some of the predictions that you might offer? I mean, especially in terms of in terms of propulsion and the things that we look at. What do you think some of the most exciting things that have jumped out at you are?
Oh God, there are really so many. Okay. So one of the big ones for me, of course, has to do with warp drive. It's sort of how I started this whole battle, from me in the 1980s. But the biggie about warp drive is how do you establish and then ramp up, turn it off? What is it? How do you make it? And when we go to something like Alcubierre, who did just an unbelievable thing that we didn't even think could be done to general relativity theory, and you look at it a little bit more closely, and you find that it's swamped with what we call negative energy. And it's basically dying for, general relativity that is dying for an explanation of negative energy. And so what Phoenix does so beautifully well is to establish what do you mean by negative energy on a quantum level. Now, when we think about that concept, we think about the Casimir effect, which is an explicit way of really getting quantum mechanics to give you negative energy and negative energy states. And so what we can demonstrate, of course, is that the Casimir effect is true. That's a given. But we can demonstrate how do you continue to derive negative energy states of particle systems. What does that mean in terms of black holes? What are you actually doing? Does negative energy get a chance to leak across an event horizon? Does positive energy, survivable inside of an event horizon? So we have all of these different manifestations. One of the modern string theory things that people are working on, like Douglas Stanford out at Stanford, but one of the things that they're working on is how do you describe the entropy of black holes such that that entropy not only goes up, it hits a boundary and starts to come down, so that entropy itself is not a problem in trying to connect string theory to black holes. And so what we're able to demonstrate is that trick that they're performing with the entropy becoming stabilized and then coming down, I think we call it the Page curve, is actually something that we predict as well. The most important thing, I think, sort of running through my head of the stuff, is what Juan Maldacena was doing in the 1990s called the anti-de Sitter space / conformal field theory duality, for which he conjectures that gravity can be divined from conformal field theories, i.e. quantum mechanical systems, by virtue of this duality that he discovered between the two theories. The problem with his duality is not that it doesn't work, it absolutely works. The problem is that they can't prove it. There's nothing about quantum field theory or general relativity or even string theory that enables for them to make that final link that says, okay, we've proven it. We can see it happens, but we've actually mathematically demonstrated it. That's what I mean by proof. And so what Phoenix does is actually show you where that proof comes from, okay? And that's our, coup de grace when it comes to modern physics, at least, is to demonstrate that, yes, exactly what Juan was saying is true. Exactly what Alcubierre was predicting is doable, and this is how you do it. Okay, so we didn't just stop at the front door of understanding Alcubierre. What we're actually saying with Alcubierre is that there are particle systems that will generate a stable warp field, and that stable warp field will travel with this speed. Okay? Or you can boost it with these types of particles to travel a lot faster. And that's the beauty about it. You can get negative energy states, which is what's required in that system, from these processes that ordinary quantum mechanical systems or theories will not easily give you, right? Because we seem to have this boundary of the no negative energy. But we demonstrate what the hell is negative energy, and how is it sometimes confusing that some systems can actually have two types of energy. One is the energy that you and I are made out of, which seems to be positive energy. And then it is completely transformable into another system that has negative energy. Okay, and that transformation alone gives that particle the ability to function as the negative energy that Alcubierre's warp drive requires. So that's what we're also saying. So there's a lot. And where we are right now is quantum chaos theory. Really being able to measure how space itself phase changes. So one of the things that comes to mind is Star Trek Voyager. There was an episode where space became chaotic. And that's really the only that's really the only connection here. So hey, even in Star Trek Voyager, they talk about it, but it's an important concept that if you make space around you phase into being a chaotic version of space, gravity goes away. It just disappears. There is no gravity. Okay, so whatever vehicle you're trying to fly will just simply float. You don't have to worry about inertial dampeners and any of those other ingenious things, I might add, but they're not necessary once you control how gravity is actually working in your system. We can even go to the point of how do you produce antimatter? Not just antimatter, the $1 billion for 10 atoms that we're doing today. We're talking about mass production. We even encounter, I don't know why, maybe we do this in nuclear theory, but we harness antimatter from nuclei, for example, right? How do we make that nucleus actually give us just the maximal amount of antimatter, whether it's positrons or whether it's, and the beauty about using nuclear matter or nucleus is that it's a safe thing to hold in your hand. It's not going to blow up because it's not antimatter. It's producing antimatter, but it's functioning as a battery, right? It's holding the antimatter in it, and it's a safe holding vessel. You touch it, you don't explode. But this stuff will produce it, right? And everybody who does nuclear science knows the atoms that produce positrons, for example. But that's what we're talking about. A safe way of both storing antimatter, getting it to give us the antimatter, and then using the antimatter for whatever purpose we so deem fit. So, but that's an excellent question. Thank you.
Wonderful. Well, thank you as well. Let me go to, let me see. I want to go to David Chester.
David!
Let me see.
How's it going?
Oh, perfect.
Great, how you doing?
Pretty good. Yeah, so my main question was if this theory is a scattering theory, then can it compute scattering amplitudes? And if so, would the methods provided by your theory be perturbative or non-perturbative?
The way that we produce the scattering amplitudes is in a perturbative way. So, for example, when you saw our exponential of the cyclic generating function, there are two ways of actually turning that exponential of the cyclic generator, e to the gt, we call it. But there are two ways of really dealing with that. One is in a completely perturbative way, for which your series goes to infinity, and the other is actually in a very finite way. So what we explore is both. But when we're dealing explicitly with scattering amplitudes, so we can do the harmonic analysis of those amplitudes, and we get a perturbative series that corresponds to it. Yes.
And
But
so,
again, we can do it in the other way as well. Mm-hmm.
So what has been computed so far? Like, can you do tree level stuff for like one loop, or like how many loop orders and what theories like have you pushed this to yet?
Let me put it this way. what we can show you is the actual, how do you derive the scattering amplitudes based on an infinite series. So we can demonstrate that. I could probably just send that to you. And what we can also demonstrate is how we don't want to do that at all, right? There are other ways of computing the field, whatever we're doing with the field. So if we're computing the spatial position, or we're computing the energy level, or whatever, there's actually a very solid, small way of doing that. But one of the important understandings is that the universe does not have an infinite number of vertices. And what's important in that statement, in this way of doing it, in other words, is the generating function actually infinite, right? And the generating function that we're turning to is the cyclic generating function, the GT, the one that's establishing all of the cycles that all of the alphabet that system has. So, but when you're creating a permutation generating function, you exponentiate the cyclic. But the point here is that if you establish that the cyclic generating function is itself not infinite, that it is a finite generating function, and we can show you why that's the case. But if you can establish that the cyclic generating function is finite, we can also then show you that the permutation generating function is equally finite. And the simplest way is to exponentiate the cyclic and get infinite terms, but that's not the appropriate way. It's not the best way. It's not the way that really you want to use. The way to the simple answer is that there's a finite extension of the cyclic generating function that we call the permutation generating function. And then we use the finite one in order to get the answer.
So it sounds like what you're saying is we're not interested in scattering amplitudes then.
Not the way that we do it in normal field theory. Yeah, that's what I would say. But there's a quicker, easier, more efficient way of getting the actual answer. Yes.
But wait, the scattering amplitude is an answer to a physics problem.
Yes,
So
it is.
you're saying, I was asking, how do you get the answer to the physics problem? And you were saying that you basically aren't interested in that problem. That's just how I'm interpreting what you're saying. I don't know.
No. What I'm saying is that there's a more efficient way of getting the answer. The first thing you want to resolve in dealing with anything in Phoenix is how big is your matrix that you're dealing with. So normally when we think about the universe around us, we're like, okay, well, maybe it's made out of vertices, and maybe at the subatomic level, the vertices are all connected up in some funky way. The idea is how many vertices are you really dealing with? And does that constraint actually tell you something about the universe that we live in? And what Phoenix says, when we show you what we mean by quantum gravity, is that the number of vertices is a theoretical boundary to the universe that we live in. There are certain, in other words, you can construct different universes by virtue of the number of vertices that you're dealing with. How big is your matrix that you're working with? And what we establish is that the points of space around you are really a bag of vertices. There's a finite, distinct number of vertices that every point in space around you has. The way we might say that, another way of saying that, is that every point in space has certain degrees of freedom, right? Certain quantum mechanical degrees of freedom to them. And those degrees of freedom for every point in space around you is fixed. And the way we fix it is at the number of vertices. So once you establish the fix of the number of points around you, if you know a way or a mechanism, and we do, for establishing how many vertices, how many degrees of freedom every point in space actually has, then that completely determines how gravity acts. It completely determines how the strong nuclear force acts. All of them get bound up into that one thing. What is gravity? What's the gravitational constant? What's the speed of light? What's Planck's constant? They're all bound up in knowing exactly how many vertices space has. So the beauty about that trick for us is, or that determination at least, is that when we look at how Phoenix describes nuclear theory, and we ask the question, what does, indium, 54 become, right? We find that if the number of vertices of space gets altered even by the least, even by one, then those answers rapidly change. And so we can measure how many vertices our space is simply by looking at all of our measurements of nuclear decays. What does, iron 56 decay into? Well, it doesn't. Well, that's important. You know, what does helium-3 decay into? Well, it kind of does. So, you know, but we can establish exactly, by virtue of nuclear decay, how many vertices, how many degrees of freedom every point in space has. And then we can show that that actual number gives rise to other calculations, or rather other determinations about physics. For example, the gravitational constant. For example, the speed of light. For example, Planck's constant. And then demonstrate with those things, you know, how the universe evolves in this limited number of vertices.
Okay, yeah, I mean, the work of Andrew Strominger shows that the numbers of degrees of freedom are increasing over time due to the expansion of the universe. And it sounded like you were saying that the material properties change depending on, I don't know. Yeah, anyways, best of luck.
Well, thank you. I appreciate that. It's good to see you again. Okay, Tim, I can't hear you.
I'm sorry about that. I hit the wrong button. I muted myself instead of. Okay, yeah, I was going to say thank you to David as well. So let me see. John Schultz had a question. John, do you want to go? Let me ask him to unmute here. And he was asking about the Alcubierre warp drive. Hi, John.
Hi, John.
Hi. Yeah, so the Alcubierre warp drive that you mentioned, maybe I just misheard. I'm not a physicist or anything.
Sure.
I'm just a amateur fan. But you mentioned that there's some sort of you have ideas on containing stable antimatter, if I understood correctly, instead of what Michael Perrone mentioned in the comments regarding just bombarding it with protons. Based on what your work and your ideas, do you have any ideas how you would go about creating an experiment to test if you can create even the smallest measurable amount of antimatter that's stable, or that's contained in a stable manner in whatever way? I don't know if that's the extent of what, I don't know how to phrase that better, unfortunately. So does that question make sense?
Oh, it does make sense. And obviously there's a lot to your question. But
cool.
the idea that I'm gathering, you know, certainly from what you're saying, is in particular about antimatter, and in particular about either stabilizing antimatter or finding a way of producing it in such a way that it can be, you know, utilized to create the warp drive. One of the things that Jeremy and I worked on and discussed a while back was an experiment for which the way that I think we like to put it was, you can float stone. And so the idea is, let me put it in this context, that we have, for example, discovered in the last 10 years that silicates are a beautiful way of taking muons and doing two things with them. One is slowing them down such that you can force muons to become atomic, and two, of producing streams of more, in this case, anti-muons. So the effect of silicate or stone is that it has this unbelievable property of doing two things that we would need in order to create antimatter atoms, or in order to create antimatter that's traveling slow enough, which is why it can create atomic forms. It's traveling slow enough to be usable to us. And so the idea behind what Jeremy and I were talking about was utilizing Phoenix's understanding of creating chaotic space, a space for which gravity has a hard time doing anything relevant, using stone. And in that type of an experiment, what you would note is that the stone would actually, under the right conditions, float. And that floating stone is something that is not terribly difficult to do experimentally in using Phoenix. It's difficult if you want to get that same thing if you're using other materials like wood, or like metal, or like carbon-based materials. And so, again, the experiments for the last 10 years have already demonstrated that silicates, like, you know, silicon dioxide, etc., have a beautiful property when it comes to those two properties. The first is slowing down muons when they are produced using the silicate. And the second is that when you use anti-muons, you can actually get the silicate to help generate more anti-muons. So it produces more anti-muons than what impinged it in the first place. So the idea there is creating antimatter that's usable. That's the whole point of that. And once you have usable antimatter, either because it's bound in an atomic structure or because it's just traveling at such a slow rate that you can actually, not, burn a hole through whatever your device is because the muons are really traveling too quickly. But the idea is that it's usable anti-muons. And again, what Jeremy and I were working on is the idea of turning that into an experiment for which you can then show that stone itself has less gravity. It can be lifted very easily under these kinds of conditions. So I hope I've actually answered your question, because I think it was a very marvelous and insightful question.
Yeah, thanks, Ken. That's brilliant. Just to add to that question, if I may,
Sure.
do you have any ETA, estimated time of arrival when you and Jeremy will actually be doing that experiment? Because that will be super interesting to check out the feedback on that.
Well, the beautiful thing about it now is that Jeremy has a whole team together that work exclusively on experimentation. So I'm not on that team only because I work almost exclusively on theory. So I have to apologize about that. But I'm sort of saying that, in terms of his team, this would be the kind of an experiment that I know that they would love working on. I haven't handed off all of the material to them in terms of everything they need to probably, really take it full force to get started. So that's on my end to be able to give that information, all of it over to them. But nevertheless, they would be the ones working on that. So again, great question.
Yeah, thank you, Ken. Very informative. Thanks.
You're welcome.
Yeah, and thank you, John, as well. Okay, so let me see. We have about 5 minutes left. Who else? I think Michael Perrone had a couple of questions. Michael, did you want to ask?
Hey, Mike.
Hey there. No, I don't think I did.
Oh, okay. You were asking about you were saying proton stability, basically, but
that was I forget where that came up, but I don't think
okay.
That was another Michael.
Oh, okay. No worries. So who else has questions? We've got just about 5 minutes left in our Q&A session.
Come on.
Well, and you've gone through so much, right? I mean, that's the thing. This is intense. I would love to have you back to talk about predictions and stuff. I think you were talking about like doing maybe a follow-up session in the future.
Yeah,
Now, I should mention that we are virtually crashing the Tesla Tech conference in our next session, so that's going to be a little chaotic.
Okay. No.
Like something like half the people who attend this conference are going to Tesla Tech, and so
Wow.
Mark said, "Well, let's broadcast live from it," and I was like, "Well, that's actually kind of the crazy thing that we would do." So yeah.
Hey, Tim.
Yeah, Michael, did you have a question?
Yeah, I'm kind of curious. There are a couple of statements you made, Ken, that made me think kind of more philosophical question.
Sure, please.
So, do you think God is a programmer, or do you think he's a Wall Street gambler?
That's good. I like that. Okay. The way I like to think about it, it's okay. That's a good one. I'm gonna say I prefer to think about God in terms of the Matrix movie.
So, well, he's a programmer then, right?
That's right. So God is a programmer, and whether you think that programmer is the architect or is what is her name? The architect and the what's our black woman?
Yeah, the old lady.
Yes.
She, I figured so.
Yeah. So yeah, I'm just, I guess I'm convinced. Now, in some ways, the programmer concept is possibly obviously a lot larger than any movie does it credit. But nevertheless, this whole way of seeing this as a program, we can literally map everything we just talked about with combinatorics directly to programming. So everything we've talked about with particle physics or with scattering theory or with relativity theory, every foundational thing that allows us to think about the universe in some equation can be mapped directly to programs, to lines of code. And those lines of code are in fact what Stephen Wolfram is talking about, but we have this other way of seeing it. So we can perform derivatives on lines of code, integrals on lines of code, so everything literally that I just said, scatterings of lines of code, everything that we've just been talking about applies directly to computer science.
So
You're going to ask it for a simulation, right? That's
Yes.
the next. That's the next step. Is are we a simulation? Yeah.
I have a little background in doing
Sure.
scattering experiments.
Mm-hmm.
One example that comes to mind is what's called X-ray diffraction.
Yes.
Diffractometer. It's basically you take a crystal and you grind it into a powder, and you put it in this thing, you shoot an X-ray at it, and you move it, you basically rotate it, and then it creates a little spectrum. Okay, and you can tell the interatomic distances and the angles between the different vertices in the crystal, and that kind of stuff. That's an example. Another example I have experienced this is a optical scatterometer.
Okay.
Where you have a laser that pointing straight down, and then it has a quad sensor in the back, optical sensor.
Okay.
And with that device, you look at what's called specular light, which is straight back. And you can tell the type of defect, a bumper. But then on the side, you have these other detectors that they basically measured the scatter light.
Yes.
You can measure the size laterally of the defect, but you can't tell the type.
Okay.
You can only tell that with the specular.
Okay.
Now, the reason I use these two examples is they both have one thing in common. They're limited to the field of view.
Yes.
Okay. So my question is, it's as you described, aren't you missing everything outside your field of view?
Say that last part one more time.
When you assume that it's like a scattering effect, aren't you limiting your data to the field of view?
Yes, yeah, absolutely you are.
Outside.
Absolutely you are. That's exactly right. Yeah. So the way that we would,
So yeah, you can get a very good predictability, but you're not measuring outside the field of view. Basically, other things can affect you.
That's right.
So, for example, going back to the optical scatterometer experiment. Okay, one way you're assuming that your surface is flat.
Yes.
Okay, but if you add a little bit of bending in the surface that's bigger than the field of view of the light, right? That you're using, you'll see some deviation from what you would expect.
That's right.
So that's an example of what I'm talking about. You can't. There's other things out unless you have the big view.
That's right.
You can't tell if your little view is correct.
Well, that's exactly right. Yes, yes. And in fact, that's the beauty about what we demonstrate is that you can divide your system into as many different parts as you want. The sort of the smallest you want to go is to a 3-part system where you account for, the things that you can't see or adequately measure as a background, right? And that background is not, it's not a background that's not interactive. The background's totally interacting with both you, the measurer, and the system that you're trying to measure. And being able to then account for this trinary type of a measurement, right? Where you just really are thinking about you and the target, but you understand that there's a lot about the target that you're not seeing, There's a lot of interactions that are not being accounted for. And then there are a lot of interactions on you coming from some other source of background.
So that kind of comes to my fundamental question, which is, you're assuming,
Mhm.
aren't you assuming the universe is three-dimensional?
No, actually we're not. It's an interesting question, definitely. But what we demonstrate, and this is something that Jeremy was probably hinting at in terms of describing where our graphs come from, or where, how are they built off of networks, etc. But what you can easily demonstrate is that the universe is really acting as a three-dimensional entity squashed down onto 2 dimensions. Not everything about the universe is 2-dimensional, but the vast majority of stuff about the universe is 2-dimensional. And
Could it then be a 4-dimensional universe squashed down to 3 dimensions?
Well, it could be if you want to represent time in that way. So what we demonstrate is that time can be represented as its own entity. It is the thing about the universe that obviously allows the universe to change in any relevant
You're
way.
saying you have space-time without time?
Space-time about time. I would say you have space that is conjoining with time, but then there are some aspects of space that don't conjoin with time. So you can set space to be chaotic on its own. Or, and this is the interesting thing that I know Jeremy was also raising in many ways, or you can set time to be chaotic or have phase shifts all on its own. So you can actually really weed them apart or combine them back together again. In fact, one of the things that when Tim was mentioning the idea of things that you're really maybe proud about, or things that seem really relevant about how you're doing this work, one of the things that lands squarely on our plate is fluid dynamics, and the idea of
What was that last word you said? Something dynamics? I missed it.
yeah, I'm sorry, fluid dynamics.
Oh, fluid dynamics.
Yeah, fluid dynamics. I'm sorry, and how fluid dynamics can actually be used, the Navier-Stokes equation, that they actually appear in this theory in a very relevant way as conjoining space and time to each other, And so the idea is utilizing, showing how, first of all, how is that connection even there? But also, how do you use that connection in order to get time to do some strange things and space to do some strange things, devoid of each other. And so it allows us to then talk about, black holes in a very specific way, or string theory applied to black holes, et cetera, et cetera, et cetera. And also to talk about, how do you get a stone to float? Because effectively you're using a sort of notion of fluid dynamics of space itself, of space and time, in order to achieve this anti-gravity effect.
Cool. So when you say anti-gravity and antimatter, you're not interchanging them, are you?
No, not at all. Not at all. Not at all.
So
Yeah, that's
I appreciate your answers, and I would like to continue our conversation, but I don't want to take up too much time.
I really appreciate it. Thank you. Great.
Your email or something in the chat, that would be appreciated.
Okay, that's no problem.
Just my own feeling is I'm kind of an analog guy. I developed with thought. I learned C in 1982. Okay.
That's all right. That's also, I guess, when Fortran HX was out.
Digital programming is cool, but I still think the universe is analog.
It's all right. Thank you. I really appreciate that.
Awesome. Well, okay, so let me do this. I want to put this back on gallery mode. Everyone, please put your hands together. Another big thank you for Mr. Kenneth Briggs and an enormous presentation. So let me see. Actually,